Thank you for taking the time to check out our work. In this video, we'll be introducing our latest research on skeleton-based action recognition (SAR), focusing on solving two major challenges that often hinder performance: class imbalance and partial labeling. In real-world skeleton-based action recognition, two major challenges are class imbalance and partial labeling. Most existing works focus on one of them, but rarely consider both together in a unified way. From our theoretical analysis, we reveal two key findings. First, class imbalance systematically shifts the eigenvalue spectra of affinity matrices. As shown in figure, class imbalance distorts the eigenvalue distributions of the normalized affinity matrix constructed from biased features. This directly compromises the convergence and accuracy of label propagation. Second, boundary samples, which are essential for learning robust decision boundaries, are often mistakenly discarded by conventional reliability measures. To address these issues, we propose SpeLER. Our method introduces spectral-balanced propagation to counteract spectral shifts and an energy-based reliability measure to preserve critical boundary samples. As shown in the figure, our spectral balancing effectively reshapes the eigenvalue distribution and leads to significant performance improvements. Overall, our contributions are threefold: theoretical insights into imbalance labeling interplay, a unified framework with spectral balance and energy-based reliability, state-of-the-art performance across 6 benchmark datasets. Now let me explain the theoretical foundations behind our method. First, class imbalance fundamentally affects the spectral properties of affinity graphs used in label propagation. As our theorems show, imbalance distorts the eigenvalue distribution, which directly slows convergence and reduces accuracy. You can think of it as the propagation process being biased toward majority classes. Second, reliability estimation is also problematic. Traditional softmax-based confidence focuses on relative class differences. For boundary samples, especially minority ones, softmax confidence tends to be low, so they are wrongly discarded. To address this, we introduce propagation energy as a holistic reliability measure. Instead of relying only on class-to-class differences, it evaluates the overall activation strength within the graph, which allows us to retain crucial boundary samples. Together, these insights form the theoretical basis of our framework SpeLER. Now let's look at our proposed framework SpeLER. The design is based on an iterative loop between model optimization and pseudo-label generation. On the left side of the figure, we start with a time-frequency enhanced network. This network extracts complementary features from both temporal and frequency domains, ensuring that minority classes are not overlooked. Next, in the middle, we apply spectral-balanced propagation. This step explicitly adjusts the affinity matrix using class distribution information, correcting the eigenvalue distortions caused by class imbalance. As a result, label propagation becomes more stable and accurate. Finally, we introduce propagation energy-based reliability. Unlike traditional softmax confidence, this metric evaluates holistic connectivity. It allows us to retain boundary samples, which are especially important for minority classes. By alternating between feature learning and reliable pseudo-label generation, SpeLER gradually improves its decision boundary and achieves superior performance under both class imbalance and partial labeling scenarios. Now, why does SpeLER work so well? From a theoretical perspective, class imbalance affects eigenvalue spectra. Our analysis shows that the eigenvalues of the similarity matrix become skewed when minority samples are underrepresented, leading to unstable propagation. We further derive that the minority proportion PM has the strongest influence on eigenvalue shifts. With SpeLER, this effect is significantly reduced, which makes label propagation much more stable and accurate. This theoretical guarantee supports the empirical improvements we see in the experiments. Finally, let's look at the experimental results. We evaluated SpeLER on 6 benchmark datasets, including NTU 60, NTU 120, and kinetic skeleton. Across the board, our method consistently achieves state-of-the-art performance, outperforming strong baselines such as SCDNet, Protolp, and SHAPMix. What's more important is robustness. Even under challenging scenarios with only 25% labeled data and high imbalance ratios, SpeLER maintains a clear advantage. We also validated generalizability. Beyond skeleton-based action recognition, our framework achieves top results on EG and other time series classification tasks, demonstrating its wide applicability. Lastly, our ablation study confirms that both spectral balancing and energy-based reliability are indispensable. Removing either component leads to significant drops in accuracy. As the spectral density plots show, SpeLER successfully reshapes the eigenvalue distribution, leading to more reliable label propagation and ultimately better model training. To conclude, our work makes three major contributions. First, we provide the first theoretical analysis showing how class imbalance distorts the eigenvalue spectra and affects partial label learning. Second, we propose SpeLER, a unified framework that leverages spectral balancing and energy-based reliability to preserve critical samples. Third, we achieve state-of-the-art results across 6 datasets and demonstrate strong generalizability beyond skeleton-based action recognition.